Hi everybody, I'm Sir Olenjolai MOCKO from United Republic of Tanzania, the beautiful, fantastic, and a great country in African continent. I would like to welcome you into my YouTube channel that called Tanzania Online A-Level Secondary Schools, and then in the square brackets is called Olenjolai M. Okay, so I don't want to take much of your time. This is session 7 of general chemistry. Okay, in case that you want to get too much details, make sure that you watch other sessions or other videos so that you can get informed about what you have to do in order to get connected into this YouTube channel, right? So I'd like just to do the quick review of what I've taught you in lecture, in session, so a quick review of our period 6, right? So in period 6, we discussed, or I taught you about experiment of what? Of Bohr's. What was Bohr's experiment, right? And then I taught you about Bohr's atomic model, finally. What is Bohr's atomic model? Means atomic theory. What theory has he stated? Then I taught you in details, and spending even almost half of the lecture of session out of period 6. I've taught you about Bohr's assumptions. How many assumptions did I teach you, if you remember? I taught you 5 assumptions of Bohr's, right? And one of interesting is say that the angular momentum is equal to the integral multiple times Planck's constant over twice pi, right? And this angular momentum is given as moment of inertia times angular velocity. So you can keep on simplifying it as well as you can. So this is very important assumptions of Bohr's postulate, and we'll be using it as time goes. Then we define about stationary state. We define about excited state and ground state. That's what we define. And then I left the homework for you. Did you do the homework? I asked you to explain briefly 7 shortcomings of Bohr's. Did you do? If you did, you could tell me in the comment section of this video, of the first video. Okay, so whether you did it or you didn't do, I would like just to continue this lecture, and I would like to start at that point. I have 7 shortcomings, but the time will not allow me to teach you all of them. So I'll be teaching a few of them. So today's lecture, I would like to teach you about shortcomings. Say shortcomings. Shortcomings. Shortcomings or drawbacks. Drawbacks. Drawbacks of 40. Drawbacks of Bohr's atomic model. Of Bohr's atomic model. Bohr atomic model. So this is the subtopic that we are going to start with. What are the shortcomings or drawbacks of Bohr's atomic model? It means that after Bohr's age, or after Bohr time, some other chemists also continued on doing investigations on the structure of atom. So when they have been doing investigations and then they proved it experimentally, day after day they found that some of the models of Bohr's were not correct. That's why you have shortcomings or drawbacks. In O-level, you learned about the shortcomings or amendments of Dalton's law, right? So here we teach you for the Bohr's and even for other chemistries. The first shortcoming is this. Bohr's atomic model does not explain, the spectrum. So this the limitations, the spectrum of multi-element. We said the spectrums of 40 multi-electrons atom. Multi-electron atom. Example, it cannot explain maybe the spectrum. Example, it can only explain the spectrum of 40 of elements that have only one electrons and their valences. Because the spectrums of 40 of hydrogen, for example, and lithium 2i or lithium ion, as I told you. So it does not explain the spectrums of multi-electrons, atoms. What does it mean? It means that this Bohr's atomic model cannot explain about sodium, cannot explain about chlorine, cannot explain about magnesium, cannot even explain about neon, cannot even explain about fluorine, because those are the materials, right? So that's the first shortcoming. Again, that it does not explain the relative intensity of spectral lines, of the spectral lines. That's why some spectral lines are brighter while others are dimmer. That's why some spectra are lighter, are brighter, while others are dimmer. Are brighter, while others are what? Are dimmer. So that is the second. So it means that we say it does not, this Bohr's atomic model does not explain the relative intensity, relative intensity of 40 of spectra, even for the hydrogens or lithium ions. What does it mean? When he did his experiment, he was just determining or examining the spectra. Remember, spectra is a plural terms of spectrum, right? So it's determining the spectra of hydrogens atoms or the spectra of hydrogens of lithium ion, right? But he didn't realize that some of the spectra are brighter than the other, or some of the spectra are dimmer than the others. So that's the one of the shortcomings. So his atomic model didn't take them into consideration. So it's very crucial in chemistry. Okay? The third shortcoming, I say that I will give you 5 and then we look for 2. So we say that no clear justification, no clear justification, okay, no clear justification was given, no clear justification was given for the quantization, for the quantization of angular momentum, okay, of angular momentum of electrons in presence of stationary state. Electrons in the presence of 40 of stationary states. Okay? So this shortcoming say that the atomic or Bohr's atomic model did not give clear justifications, okay, concerning the quantizations of angular momentum of 40 of electrons in presence of stationary state. What did he say? He just said that the angular momentum is the integral multiple of integral multiple of Planck's, or with Planck's constant 10 plus 12 pi. So he didn't justify, it means he didn't show that the issue of quantizations, because he said that the energy quantized. And against that, we will show that this man also proposed that the energy of electrons in orbit is equal to this formula, which will derive it soon. Right? So that's the third shortcoming. In case you have questions, don't hesitate yourself to ask in the comment section. The first justification, or the first model, we say that Bohr suggested that the electron move in circular orbit. Okay, move in circular orbit in 2 dimensions. So you say that the electrons move circular form in 2 dimensions, while it has been proved that in the quantum mechanical atomic mode that we studied later, that the motion is in 3 dimensions on elliptical path. So he said, Bohr suggested that the electrons move in circular orbit, right? So you say circular orbit means that he said that this is the orbit. This is the sun. Not the sun, this is the nucleus, sorry. Nucleus, here you have electrons in this orbit. Okay, so he said it is circular and also it is 2 dimensional. While experiments show that the shape of the paths of electrons when they are revolving nucleus is not a circle, it's a sphere. Right? It's elliptical. So this is, you have full stop here. So we say that in the experiments proved that the path or the orbit we say that the orbit of electrons prove that the orbit of the electrons is not a circle, but it is what? It is a sphere. Or we call it elliptical path. Elliptical path. And its motion also and sorting, its motion is in 3 dimensions. Right? So you say the orbit of electrons is what? Is circular, which is not true. And then you say again, the motions of they move in circular orbits in 2 dimensions. While experiments show that they move in 3 dimensions and so forth, but also they follow elliptical paths. Say elliptical paths. So let me give you the 5th shortcomings of Bohr's. Again, we said that the Bohr's atomic model, does not explain how covalent bonding makes a molecule, how covalent elements, for example chlorine, how covalent bonding makes a molecule stable. Makes a molecule stable because the model does not recognize the existence of some energy level. Because this model does not recognize the presence of what? The existence of sub-energy levels. The existence of 40 sub-energy levels. Okay? So So Bohr'S does not explain how covalent bonding, I'll be teaching you chemical bonding, makes a molecule. How does it make a molecule stable? And this is because this model does not recognize the existence of 40 sub-energy level in the molecule, right? So make sure that you look for the 6 should come in and 7 should come in. So this is your homework. Okay. Okay. So if that's the case now, I would like to take you now into the computation platform. Bohr's established this mathematical relation that can help we who are young chemists to understand the concept. So now I want to teach you, or let us take the large part of this lecture right now in the subtopic, we call it energy associated with an electron moving in particular main energy level. Moving so energy associated with an electrons moving in particular main energy levels. Main energy level. Okay. So we'll be spending the rest of this lecture on dealing with this mathematical relation that has been developed by Bohr's. So simply the question, it might ask you that derive this equation that the energy in the orbit is equal to what? Energy in the orbit is equal to negative 13.6 electron volt over n squared. So we want to derive this formula. Right? So derive, what do you say, will follow a number of steps. The first step for this situation, we say that consider we say that the first step, consider an electron that is, okay, consider an electrons in hydrogen atom So consider an electron in hydrogen atom. Okay, in hydrogen atom, that is jumping from the higher energy level jumping from lower energy level on the lower energy level, okay, to the higher energy level with associated energy of 40 E1 and E. Don't get confused with that sentence. Let me draw what I've written there, then you'll understand. Easy. Suppose that here we have energy level for hydrogen. Listen carefully. Listen and watch carefully. When it reaches to the infinity, n is very large, it will be infinity because it will be increasing from 1 continuously. Okay, so what do you say here? Listen carefully. Suppose initially an electron was in ground state. This we call it Lyman state or Lyman series, or we call it ground state, while all the remains we call them excited state. Right? So this is n is equal to 1. And then we say that suppose the energy of these electrons here, it is E1. Right? Is E1. When these electrons want to jump to the another energy level, which is what? This is Balmer. This is what? Bastion. This is bracket. So when to jump, for example, from here to Na of the higher energy level, then suppose that to jump with energy known as E, and the integral multiple by that time will be n. So E1 will be corresponding with n is equal to 1 or with n1, for example. Suppose that this is n1, right? Are you together? N1. So the corresponding of A1 is N1. Corresponding of A8 is what? N. That the first state. Or this the second state. Consider the figure below. Okay. So if that's the case, he said that we go for the second step. We follow a number of steps. The second step, we say that we recall the rebate. Rebate. Recall the rebate equation. Right? How does it state? I told you in the previous lecture. Rebate state that one of our wavelengths is equal to rebate constant. Then we have 1 minus N1. This is the lower energy level. Right? So this is what N1 minus what? 1 over N2. But these are squares. For this case, because n it can take any value, and this is the operation that we have. So it's the 1 over wavelengths. This is the rebate constant, 1 over N1 square minus 1 over T over N. Okay? So then, we don't need even to simplify anything else. This just we call equation 1. We need that reference. Again, we go for the second, so the first step. We say that you have to recall the Planck's constant, or the Planck's equation. Call the Planck's equation. Okay? Call the Planck's equation. We say that energy is the proportional to the frequency. Right? So for this case, because the electrons will be jumping from one energy level to another one, then we have the change of change of energy. So the change of energy for this case is equal to Planck's constant times frequency. All together. And this change in energy depends, because here we subtract this one. So it means that about so this one, but changing this one is energy, the higher energy, which is E, minus the lower energy, which is E1. Right? Very important. Why did I remember? If you write E1 minus E is wrong. How I told you that in the beginning, in this figure, E, the capital letter E, is corresponding to what? The everything that E, this one that is corresponding to N. Where do you write E N? Right? And then she said, I told you that E1 should correspond to what? S. Represented by N1. S. Right? So then, if that's the case, you say that now, the energy difference is equal to, change in energy, Planck's, or Planck's constant, Planck's constant times 30 is frequency. Okay. Yeah. So energy. So energy 1 is equal to what? Is equal to Planck's constant times what? Frequency. Right? But also, we say that the speed of light is equal to wavelength times frequency.